these are sort of personal reasons, but the Hauff homology of category perfect complexes on DG is just zero algebraic K-theory of so sort of, well, that's a personal reason. The second reason, well, this is easier to compute. It's easier to compute than sort of the K-theory spectrum. So if you want to have a derived invariant, you might want to consider an entire K-theory spectrum instead of truncating it. But the higher K groups are generally considered hard to compute. So the third reason is this Hauff homology is geometric. So sort of what I mean with that, so this is something we'll talk about, but the Hauff homology is some sort of derived stack or space or whatever should be given by global functions on something called a derived group space. And so this actually has sort of mathematical consequences. It's not just sort of nice for interpretive reasons. For example, just sort of formally, you can get things like, I don't know, Hauff homology. So I'm going to stop writing perf. In this talk, everything's going to be perf. And I might have to assume this at some point, but, so the Hauff homology is sort of these fiber products. This should be something like the X groups over the base of the push forward thing upstairs. And these kind of statements are nice. You have like functors and adjunctions, and you can get sort of categorified statements. Okay, and then, well.
What does this say? It says the fiber product of X with X over Y?
Yes.
Okay.
Okay, and then the fourth reason, so sort of this is, HP is sort of, this isn't really a general theorem yet, but it's known in some special cases. So the periodic cyclic homology is generally believed to should be sort of topologically invariant. Right, so for example, the Hauff homology of the algebra of dual numbers, you just try to compute it, it's not going to be the Hauff homology, it's just the residue. This is easy exercise, but when you sort of make this periodic, it does make this becomes an equality replacement. Okay, so let's start by myself. So first, I'd like to review what Hauff homology is, taking sort of the viewpoint that sort of instead of Hauff homology of an algebra, I'll be taking Hauff homology of a category. So, computing them, well, okay. So let's say C is a stable, has to be small infinity category. Right, you can also think of it as a small DG category. So what the homotopy category of C is just going to be a small, probably have to say triangulated. So homotopy category is just going to be a small triangulated category. So if you're not familiar with sort of DG or infinity categories, you can just think of triangulated categories. But somehow to make the definition make sense, I really do need to work in this context. Okay, so so there's this thing called the incompletion of C, which is, so I won't really formally define it, but you want to think about it as sort of formally add all filtered colimits to C. So the sort of main example that you want to have in mind is sort of if C is a perf. So this, if A, so say A is an algebra, and this is a category of like finitely generated free complexes with, with free terms or summons of free terms. And so in a C, C would just be A modules. Right? So this is a small category, like this, the objects in this category form a set. Right? They're finitely generated, but the objects here definitely don't form a set. Okay. And there's this fact, so this is the fact, so the categories like that look like this are dualizable in some sense. But really, the only thing I'll need to use about this is that in all examples that we'll consider, right, I'm just going to want to sort of identify, there's an equivalence between this functor category. So functors between this sort of these two large end of functors of this large category. And so there should be some equivalence like this. And in all our examples, we're just going to identify it. So I don't really want to go into the general theory, but this is sort of like the key thing that we need. And so now I can define Hopf homology.
That means colon preserving, or?
Yeah, L means filtered. I guess also the all. Okay. Okay, so the definition of Hopf homology is it's going to be you take the co-evaluation. So the co-evaluation lands in here. It's just identity map. Then you use this isomorphism. You apply the evaluation, which brings you back and to sort of the evaluation goes from this category to the category of vector spaces. So I should say, when I say vector spaces, I really mean chain complexes. So it's like DG vector spaces. And this is an object, so this is an object, which is really which you can also take homotopy category and okay, that didn't really do that. Okay, so this is my definition of Hopf homology. Some examples. Okay, so we have some algebraic examples. So if I take my category to be a turf, right, then the dual. So I didn't say what a dual is. This is a dual. The dual will be a turf opposite category, which is the same as a opposite category turf. And the equivalence just takes a module and sends it to the dual. Okay, but it turns left modules into right modules. So Morita theory tells us what this thing should be, because we know that sort of functors from A mod to B mod that preserve colimits should be given by A or B modules. And so the co-evaluation is given by A as a bimodule. And then the evaluation is given by the functor A tensor a bimodule over A tensor yacht with A. So then Hopf homology of the perf is this thing, which is sort of the usual Hopf homology that you'll find in most of the textbooks. Okay. So just sort of an aside, this kind of gives us an explicit description of the Hopf homology and sort of, so for if you have any category, right, so C is a sort of category, there's an explicit modeling going down for the Hopf homology, which is, well, the Hopf homology of C, right, it's so you're given by this large complex. So you're gonna just write it. there's x0 and x1, there's two objects. And I think you get the idea. So after this, there's three objects, etc. So this is an explicit model. It's not a very useful one for computing because there's just way too many objects. But you can replace sort of the set of all objects with sort of a smaller set. I'll call it G. Is G generates. So for example, if your category is a perp, sort of the set with the free module generates. And then, well, when you write down this complex, right, this thing is just, it's computed by the cyclic bar. Cyclic bar. Because there's only one object, so there's all the direct sums go away, and the homs between A and A is just A, or when A is an element. Here's one example. Second example, we'll sort of take something a little different. Let's take C to be sort of the derived category of G representations. So let's say G, I reused G, so let's say H. Okay. H representation, where H is a reductive group. So in this case, it's a reductive group, so it's a semi-simple category. So my generating set is just going to be the set of irreducibles of H. This will generate a category. There's no interesting homs between any of these objects, but there are a lot of them. I mean, there are a lot of objects. So what I end up getting, right? This will be a direct sum over sort of the irreducibles of the sort of cyclic complex for just an object that has just the identity morphism. So those things are going to look like the homology of K, or your field, I guess. And that's just so this is a vector space in degree 0. It's a direct sum, sort of one copy of your field for every irreducible. So the second example, the second class of examples, this is the one I'm interested in, are the geometric ones. So let's say, in this case, the category I want to think about is something like perfect complexes in a scheme or a stack. Okay. And then the dual, the opposite category, and this is equivalent to the current X, created by the same kind of thing. So if I have a perfect complex, I can always send it to its dual, which is the Shisi hom. Okay, and now sort of there's a paper by Benzi and Francis, which sort of identifies the dual eigenstructure. So this thing. Y. Okay, and I won't talk about this function, or this equivalence, but over here the equivalence takes sort of a sheaf on the product and sends it to the integral kernel that's determined by that sheaf. So this is so it's going to be the push forward to Y, pull back for X, and then you yeah. So is this familiar? Well, so for example, right, if x equals y, right, there's your favorite functor from quasi-coherencies on x itself is the identity functor. So, okay, well, the identity functor, quasi-coherencies on x, is just given by the integral kernel for sort of the push forward of the diagonal. Right? Because if k is just the structure sheaf on the diagonal, and I pull something back and I tensor, well, you're just gonna end up with, I think you probably can do some functoriality, but you just end up with, right, dash supported on the diagonal, and when I push it forward. So this lets us sort of identify what the valuation and the co-valuation are. So the co-valuation, so let me draw a picture. So the point. Okay. So here, P is just going to be the sort of projection to a point. X, this is going to be the diagonal map. Okay. And so the co-valuation is the structure sheaf on the diagonal, so it's another way to write that is the map, is the functor given by pulling and pushing. And then the evaluation should be the dual to this, so it's going to be the functor you get by pulling and then pushing along this side. So the Hopf homology of curve x is just the composition of these functors. So it's this thing. So when I pull, the structure sheaf, I always get the structure sheaf, and this is just going to be global sections. So it's global sections on x of so this is the Hopf homology. And every functor is derived, that I write down. Every functor has to be derived. Okay. Now, at this point, I'd like to introduce some derived algebraic geometry. So maybe, so what I would like is if there were sort of, if I could take some sort of fiber product here. I'm just going to write what it is without explaining it, but I will explain it later. And it'd be nice if instead of pushing and pulling here, I could sort of do a base change, pull and push there. Right? And in sort of classical algebraic geometry, you can't do base change along non-flat maps. Right? And none of these maps are very far from being flat. Right? But sort of in derived algebraic geometry, there's this notion of say taking a derived fiber product. Right? So this is a derived fiber product that has base change. And I mean, when you sort of write down these sort of easy affine examples, this isn't so surprising because you're just, I mean, this derived fiber product just means on affines, this thing is just a tensor product. Right? So instead of, well, when I take a tensor product, I need to write down the resolution if I want to derive it. So in this case, well, you want your resolution to just still have a ring structure. So that's sort of the very short version of what this thing is. But we'll do an example. But the upshot of this is that if I apply base change, right, instead of pushing and pulling here, I can pull and then push here. So this thing is global sections on the loop space of the structure sheaf of the loop space. Right? When I take the structure sheaf of X and I pull it up here, I get the structure sheaf of the loop space, and then I can push it all the way down. So this is just functions on this loop space, whatever that is. And I'll talk about why it's loop space. So far looks okay. So definition. Part 2. So the loop space of X is going to be maps from S1 to X. So this is an internal mapping stack in the category of derived stacks. So I guess we don't have to just believe this exists, but so I'm just going to argue sort of that this is the same thing that I've written here. It can be computed by this product. Right? And one way to sort of see that is if you also believe that this derived mapping stack should take co-products in the source to products outside the source, well, then we can write this S1 as a homotopy push out. So this is I can S1 is the suspension of S0. And, well, the homotopy push out, the suspension can be written as the homotopy push out, where I sort of send a point. Okay, so one way to see this is when I take a homotopy push out, I want to replace one of these maps with a cofibration. And the cofibration I replace it with is I turn the point into an interval. So then what this is saying is I have an interval, so this becomes an interval, and then I can move it at the ends. And then just formally, this expresses the loop space as a fiber product. So what is a fiber product? Well, maps from a point to X are just given by points to X, and then maps from 2 points into X given by X cross X, and this map is diagonal. Okay. So that's why this thing is. Well, that means the loop space of X is in the spectrum A, tensor A. So I need to sort of resolve this in a way that gives it a sort of algebra structure. And it turns out, so the cyclic bar complex has a shuffle product. I won't write it down. It's in, I think it should be in line order. Okay. So second example is if I take X to be VG, so the loop space of X is so the sort of this fiber product. It also computes the inertia stack. Okay, so it's going to be the inertia stack. Sort of the classical inertia stack in algebraic geometry. And I guess it's a sort of algebraic geometry exercise to show that the inertia stack in VG is the adjoint quotient. And okay, so now the only question is why is there no derived structure? Right, so there's no derived structure because the diagonal map of VG is flat. If you take an atlas for VG cross VG, pull back this thing should be completely messed up. Okay, and that means okay, so this actually allows us to compute Hopf homology, because the Hopf homology of per VG is functions on the loop space, and functions on the loop space are sort of global functions on the adjoint quotient, which are sort of polynomial functions on G when you take G invariance. And this thing is a big direct sum. So this is by the Peter-Weil theorem. This is a direct sum over their irreducibles. It's a sum of the irreducibles tensor their duals. You have to take invariance. And sort of in V tensor V dual, there's only one there's a single, there's always a single trivial representation. So this is, and this kind of agrees, this agrees with the calculation earlier. Is there anything? Okay, so now the example that I'm most interested in is when we take y x to be a general quotient stack. And in this case, it's the sort of answer is a little, well, I mean, it's a little more difficult. So, let's sort of, I want to sort of start get an idea, a feel for what this thing is. So this loop space, you can write it as a fiber product, as a derived fiber product between so this is the diagonal map, and this one's sort of the action map times the projection to the sort of center. And everything's sort of equivariant over G. Let me not write that. So there's sort of a mod G everywhere. And sort of this thing, the K points, the K points of this thing are given by pairs.
There's some x's are supposed to be y's.
Yes, all of them. Yeah. Okay. All the x's are y's. Right. So this is so they're pairs of points in y and points in g, such that g fixes y under the average. So unfortunately, g's and y's are similar. Okay, so another way to sort of see this thing is there are natural maps of the loop space of PG, exactly quotient. So I'll call this sort of loop space of P. And there's also an evaluation map, so any group I can evaluate the identity, and this gives me a map of y mod G. And sort of the fiber for this map over, say, point G, this is sort of to be like forget equivariance and whatever. This should just be the Z fixed points is Y, G fixed points is Y, and the fiber over point in Y is just a stabilizer. And, well, we know that the Hopf homology, again, of this category, is functions on the loop space quotient stack, but it's not super clear like how we get a sort of explicit answer to this. Okay, so now I need to introduce a few sort of variants of loop spaces. So I'll make a definition. So this, the L hat X, this is going to be L of X completed at the constant loops. Right, these are called formal loops, formal loop spaces. So this has good properties. Mainly sort of functions on it, or the structure sheaf on it, is smooth local. Okay, so this is good if we want to understand it for stats. If we understand it for schemes, which I'll claim that we do, then, and knowing it's smooth local, that gives us a way to understand it for stats. Because we're ardent stats, at least, because ardent stats have a smooth cover. I'll also need a uniform loop space. So this is, I mean, the sort of the definition probably should be something like this. But So you can think about this as you complete that uniform. And I'll sort of talk about this more later, but I just want to set it up for now. So this little idea is that because we think we understand formal loops. Okay, let's do some examples. So examples. So X is a scheme. Right? All these notions coincide. So the formal loops are equal to the unipotent loops are equal to sort of all loops. So these are all the same. And if X is G, then the formal loop space is you complete identity in G and take the quotient. The unipotent loops are you complete at the unipotent cone, take natural quotient, and we've already computed that the loops are just that quotient. Okay. So the point is, we sort of understand loops, sort of the Hopf homology of the scheme. In the smooth case, it's just given by Hopf. So sort of HH here is given, you can compute it by sort of, at least you can compute it by HKR, Hopf constant Rosenberg theorem. And HC and HP are also understood, we just end up with a Drama complex. So, on the other hand, these things, so this thing is also sort of computed by a Dirac complex because it's smooth local, but these are not. Right, so sort of, I guess, knowing things about schemes doesn't really help you compute sort of global loops.
What's the U here?
U is the unipotent.
Oh,
Yeah. Okay. So this motivates this the theorem state. So if X is smooth, it's reductive. Right. The claim is that the formal loops, and let's say Z is a semi-simple element of G. So the formal loops of the classical fixed points of the stack. Okay, so there's a map, I'll construct it later. Okay, so this, I have to define what this is. But this thing is the loop space of the quotient stack. Then I'll take the fiber product over the loop space of BG. Okay, so the loop space, the map from the loop space of the quotient stack to the loop space of BG is representable by schemes. And then I'll sort of take the fiber, I'll take sort of a fiber over a formal neighborhood.
What is what does it say in the first term?
Here?
Yeah.
Yeah, so this is formal loops. Pi naught means take the classical truncation of the derived scheme.
So X is derived?
X is smooth, so X won't be derived. But I'm just sort of trying to remove ambiguity by saying the classical invariance. So,
But then XZ, what is XZ?
Fixed point.
How is XZ derived?
So you can, yeah, you can sort of take so this is sort of the action, the graph for Z, the diagonal, and take a derived fiber product, it would be derived. But sort of, I guess I'm saying sort of whatever your definition of fixed points is, just take the classical. There should only be one thing called a classical fixed points.
So pi naught is just the usual fixed point.
Yeah, yeah. Yeah, so this is just a classical. Okay. Is this?
What does the theorem say about
That's
that?
nice.
That's a definition.
It's a nice one. So I'm going to draw a picture. This goes to 5:30, right? Okay, so the picture. So let's take G to be a torus, and let's say it's two-dimensional. And I'm just going to draw X. X is just going to be this space, and this is sort of a picture of the orbit. So there's two fixed points, and a one-dimensional orbit, and a generic orbit. And I want to take the loop space of X mod T. Should look like something like this. So
X is P1?
no, X is just this sort of blob. I mean, it's a toy. I mean, X is it's some scheme where sort of you have
It's a tonic variety or
Yeah.
scheme which compactifies the torus by 2 points. Two-dimensional torus by 2 points.
So if the problem is maybe this doesn't exist, I'm not sure if it's compact. I just, you know, it won't be important that it's compact or not.
Or even if it's not compact,
Right.
it doesn't exist.
It does, well, if it doesn't exist, any sort of scheme that has.
I think it's blow up at the plane minus some points, right? Or minus
But that's constructible, it's not a scheme.
Well, sort of, it's only supposed to be kind of a toy picture. It's
Okay.
not going to be very important.
Okay.
Yeah, so, okay, so this is going to be a map. I mean, yeah, it's just a toy, not really an example. So, loop space of BT is T cross BT, right? Because T acts kind of trivially. So T, I'm going to draw it in a sort of linear way. First. Okay, so here's identity. Right, so the fixed points of the identity is everything. Let's say I'm going to draw there'll be a special sort of subgroup of this thing, which is a stabilizer of a point in this one-dimensional orbit. And there's a projection sort of going to X, and over these fixed points you should get all of T, right? So there should be 2 copies of T, and then sort of next to this one-dimensional orbit, you kind of get this component. The drawings are not so big, but
Also, you do have a one-dimensional.
sorry.
So I misunderstood what X is.
Uh-huh.
So X has one two-dimensional orbit, one one-dimensional orbit, and 2 zero-dimensional orbits.
Yes. Okay, so this is a picture, and let's say Z is this point over here. It's in your sort of special subgroup, and so there's going to be a map going into there. So the fixed points of Z, right? So above here, it's just going to be this sort of squiggle. Right? And if I take formal neighborhoods, I'm going to end up with extra sort of a 2-dimensional disk here with kind of a sort of family of 1-dimensional things between them. And, okay, so the loop space of this classical fixed point thing is going to look like this. There'll be right? And what it's going to do is it's going to map this map. What it should do is it maps the identity here over Z. Right? It should move the fiber over E to Z. And yeah, so it's just going to map it. So that's the picture for the map. I'll write down a definition.
over each point in D cross DP, you're drawing the fixed locus of that
Yes.
torus point.
Right. So generically, these are the only fixed points. So that's where you have points. Over this sort of special subgroup, one-dimensional subgroup, this one-dimensional, the fixed points are fixed, and also this one-dimensional orbit. So it's a one-dimensional orbit, so there should be a one-dimensional stabilizer. 2 minus 1 is 1. And remember the identity of it. So then this is, yeah. So in this case, I drew the picture to have finite many orbits. So it's, I guess it's a fact for smooth things, with the loop space of x mod t, if there's only finitely many orbits, there's no derived structure. So when there's no derived structure, this is maybe a more classical statement. But if you had sort of infinitely many orbits or sort of families of orbits, you know, there would be some derived structure in this picture that I couldn't build, that I don't know, that I didn't or can't run. So that's sort of part of what has to be somehow part of it. Okay, so let me. Well, I'm shorter on time than I thought, so I won't sketch the proof, but I'll at least tell you what this map is. So this map. You can factor it. Right, so it's the composition of these three maps. So this one is going to be sort of a multiplication by z map. And the only reason this exists, right, is because z acts trivially on sort of on this thing, right? And z is central. Otherwise, I mean, in general, there's no such thing as multiplication by z. It's not going to be equivariant. It's sort of an equivariant map. This thing is just loops of a sort of closed immersion. So this map is a closed immersion, so loops of it. And this will be sort of a, I mean, this is loops. There's a map x mod g, x mod subgroup to x mod g. There's a map, and that's just loops of that map. And this one, this map will be a tall sort of. I can write all these maps down without taking formal neighborhoods. And this one will be a tall, so it's an isomorphism of formal neighborhoods. So if you want to prove this, you would only have to show that this thing is an isomorphism. And, well, this one turns out to be a local isomorphism. So the way, so the reason, say very, succinctly, but so this thing, right? This map, you can write it. You can write down these two as fiber products. So x, I assumed x is smooth. So because x is smooth, the diagonal map is local complete intersection. So I can check this on local rings. This is a local complete intersection. And so I have a sort of, I'm just going to say it in words. If this is dimension n, right, I can sort of choose, say, some R generators corresponding to lifting generators for the local rings here. And then the rest of the generators are given by cutting out this. The equation are given by just an equation that does this out, right? So somehow, right? So if this is like, so over here, there's sort of like n sort of derived equations being used. Right. So what I do is I resolve this map, right? So this is a codimension n map. So there's n sort of derived equations I'm imposing my proposal resolution. Over here, let's say this is dimension R, right? So here there's R derived equations, and then n minus R classical equations. Like the classical equations are imposed when I say like pi naught of x. And the argument is that these classical equations will match up with some derived equations over here, and you just have to check that sort of they're related by something. I mean,
This is exactly why you're using the Z semi-simple.
yes. I think to get the Luna slice theorem. Yeah. I also needed it here. Maybe.
And that too, yeah.
But that's sort of a short version of the argument. Somehow. Just reasonably satisfying.
Why did you want to put on the first map?
Sorry?
So the first map seems, I mean, what convention do you want that first map for?
Convention.
Well, I mean, like, it doesn't change the domain of the map, right? If you put on that first.
Yes, but it's not.
And everything else is still an isomorphism of together.
Well, it's not an isomorphism everywhere. It's only an isomorphism at some points, right? I'm taking local points in the image of the thing I'm computing at. That makes any sense. Like this is an isomorphism over points where I take Z here, not the identity.
So it's just a,
Right.
just a domain.
Right. It's not a global isomorphism. It's like a local isomorphism along the closed thing. Yeah. So. Okay. So now the goal is the goal is to understand Hodgkin homology or periodic cyclic homology. So given this, one might hope for something. Let me write the thing we might hope for, and then tell you that it doesn't work. So we might hope that Hodgkin homology of this thing, when I complete it as sort of a Z downstairs, it's the same Z as over there. You might hope that this is something like functions on the sort of formal loop space of, right? It's just a thing that I produce over there, and this is wrong. So it doesn't work out, and you can just see it on the level when you take that to be a point, it's already evident, right? So this thing's a vector space. So if we want to complete sort of ideal in a vector space, that means we're talking about affine, something affine, right? So when S is a point, we have the loop space of VG, and if we want to complete sort of algebraically, that's geometrically that corresponds to completing at the spectrum of the global functions of this thing. This is G mod G, and this thing is the GIT quotient. Okay. So you have a map from the stack quotient to the GIT quotient, and if I take my favorite semi-simple parameter down here, the fiber that sits over it are things of the form SU, where S is in the orbit. That's like nice, but U can be any unipotent element. Okay, so this is so somehow like the thing that I'm getting isn't when I complete. I'm not really when I do this completion. I'm not actually completing it. I'm not taking formal loops. I'm taking like unipotent loops. Okay, well, there's a corollary. It's the same theorem, but you replace the formal loops with unipotent loops, and it still works. But this is still not good enough. Well, so it is. So then, okay. So it seems like this might be good enough because then we know this is just functions on unipotent loops. Right? But this is also not satisfying because somehow I don't really understand unipotent loops. Right? The whole point was we wanted to get things down to formal loops because formal loops are so global. They were something that you can kind of understand on a cover, but you can't understand unipotent loops on a cover. So the solution, or I don't know, solution, sort of the answer is you replace HH with HP. And this is kind of nice for two reasons. Sort of first, even in the case of a scheme, right, HP of X is the Betty cohomology of X.
Sorry, did you mean to write HH in the line above?
Yes. Thanks. Okay. So periodic cyclic homology is known in the case of X as a scheme to just compute the Betty cohomology. This is even in the singular case. In the smooth case, it's sort of just HKR, but there's a theorem by Bargat-Bott. He sort of does it in a general case. This is his derived Drama cohomology. And okay, so this is nice, but also here this is another thing we proved is that the periodic cyclic, or rather the global functions. So the HP is it's an invariant we get from Hopf homology by doing the take construction. So global functions on the formal loops, when we apply the take construction, is the same as functions on the uniform loops applying the take construction. So this is like a kind of a technical. The argument is a bit technical, but the idea is that when we apply the take construction, when we do this sort of periodic construction, it kills the difference between uniform and formal loops.
What does this look like for BG?
Sorry?
What does that statement look like for BG?
Right. So for BG, and what this says is sort of okay, so if G is reductive, I think this is, yeah, so it says like, if you take sort of this thing, right, and you complete, I mean, there's like an ideal for the identity, you complete at that thing. It's the same, that sort of identity, it's the same as sort of this, where you complete at identity, coming up into it's uniform. So maybe the difference is clear if we take a unipotent group. So if if G is unipotent, right? And we take BG, right? So the formal loops are going to be, I mean, you complete at identity, so it's going to be something like, whereas the unipotent loops, all the loops are unipotent. So this is all of them, right? So U looks like affine space. So the difference between like formal functions and sort of global functions. And the map in general will not be an isomorphism, right? Like completing, I mean, let's say U is a abelian or something, right? Then this thing, I mean, say U, I switched notations, right? This will be something like formal functions. This will be something like polynomial functions. And these are just non-isomorphic. But when you apply the take construction, this is not quite true. They're sort of, right? The BGA has some derived thing. That's sort of important. This is coming from BGA. But when you sort of apply the take construction, there's sort of a differential that kills both of these variables. And somehow, when you apply take, you just get two periodic, sort of two periodic copy of the trivial K. Okay, so I'm pretty much out of time, but maybe I'll just state the sort of. So putting sort of all the pieces together, what we get is that the periodic cyclic homology, this thing when I complete it at C, is just the Betty homology into periodic fixed point stack to periodic. I guess I have like 30 seconds left, so I can talk about future stuff. So future, what I'd like to do is I'd like to sort of, so right now I'm assuming X is smooth. All the arguments require X to be smooth. I'd like to somehow generalize to the singular case. And then there's some questions like, coherent versus perfect. Which ones do you want? I mean, I would like to study for the coherent sheaves. So in that case, talk about functions with distributions. And also, so this is sort of maybe a more far off generalization, but maybe a more immediate one is sort of, you can get, even in the smooth case, some topological variance results for HP of quotient stacks. Because what you can do is if you, this is a topological invariant. So if you can check at sort of completions of close points over VG, that some map is an isomorphism, you would know, well, you don't know that it's an isomorphism, well, right? You would only know that if it was coherent. So well, maybe if we can show that sort of HP is coherent, HP of X mod G is coherent over HP of VG, then you'd be sort of no, I'm not sure.
Okay. Thank you. Any questions? In the singular case, do you expect for either version, either the coherent or the perfect one, do you expect to have to modify the definition of the unipotent and the formal loops by putting arc condition at the singularities?
So I don't know. Yeah, I don't know. Well, so the first thing I wrote down about sort of the formal loops being classical fixed, that statement is not true in the singular case. So the one thing I thought of doing is trying to replace the classical invariance with something between classical and derived invariance, but I'm not really sure. That's
So you don't even have a guess right now?
Well, the guess, so the guess would be that to avoid working with, so the guess would be to try to embed a singular thing into a smooth thing, and then get some statement on the level category. So if you can identify the subcategory that this thing is, and then, well, also sort of coherent sheaves on, if you can somehow identify the subcategory, maybe you can get something, and sort of coherent sheaves on formal loops, that should be equivalent to D modules on sort of the thing without the loops. So this is a work in progress right now. I don't know, somehow try to leverage that. But at this point, it's very speculative.
Have you tried to look at how any of this looks if you try to formally just transport the statements you have to statements about the Deram stacks? Because we have really two different models for the homology. One is given by functions in the loop space.
Yes.
The other is given by modules of the Deram stack. So, and there is a way to actually relate them by doing a to infinity stack. The to infinity loop stack actually specializes in both. So, in principle, any statement you make in this context should give you at least, in fact, you can make this a mathematical statement. Any statement you make in this context will transport to a statement for the Deram stacks. But even if you don't, carry it through the transport, you can probably just guess what the statement will be in the Deram language. Have you looked at that?
No, I haven't. But maybe I don't quite understand what. This is true for in the case of stats completely?
For any.
I don't know about this, but I'm happy to hear about it.
No other questions? Well, let's take the question again.